Alright, moving onward. So, we're going to be talking today about collinearity, which you guys will learn what that is. Betweenness, you probably have an idea what betweenness means, but we're going to define it a little bit more specifically for geometry. In this class. So starting with the definition for collinearity. Points that lie on the same line are called collinear. And you may notice that like line, the word line is within that word collinear, that you can draw one single line that goes through all those things at the exact same time with one single line. That's what collinear is. Points that are not on the same line, as you figured, probably would be called non-collinear, or they are not collinear, non-collinear. So they're not on the same line, then that would be non-collinear. So for example here, what are some examples of some collinear points? There's all kinds of collinear points here, like H, G, F, and D. You can draw one single line that goes through all four of those points at the same time. Thus, that group of 4 points, they are collinear with each other. Another set of points that are collinear. Let's see here. If I check out like, how about C, D, and E? Those 3 points are collinear with each other. You don't have to have 3. You don't have to have 4. You could even have 2 points. Like A and F. Those are collinear. What about points A and G? Would they be collinear? Collinear. You have to be able to make one line that goes through both those points simultaneously. It's kind of a tricky question, but yes, actually AG is collinear. Even though there's not a line drawn between A and G, I would be able to make a line that goes through A and G at the same time. Thus, A and G would be collinear. Okay, so just because there's not a line between the points doesn't mean that they're not collinear. It just means that you can draw a line that goes through those points. Any 2 points that you can imagine, you can always draw a line between any 2 points in the entire universe. So, thus, any 2 points are always going to be collinear. What are some examples of non-collinear points? Some examples of non-collinear points, well, I think you guys could probably come up with a couple, so see if you can't do that. For a point to be between 2 other points, the points must be collinear. Okay? It doesn't make sense to talk about between if the points aren't even collinear. So for example here, is F between A and E? Is F in between A and E? Yes, it is. How do I know? Because it's between A and E, right? Like I shouldn't have to explain that. But on top of it, like it's also collinear with A and E. Versus if you look at is F between C and E. So if I switch up A and want to talk about C, is F between C and E? No, F is not between C and E. Yeah, it's kind of like somewhere there, like not quite further from C, but not quite further from E. Well, I don't know what the heck I'm getting at there. But essentially here, like it's not collinear with C and E because it's not on the same line, or they're not collinear with one another. So those are not collinear because they're not, but it's not between because they're not collinear. So that doesn't make sense to talk about F being between those. D, on the other hand, would be between C and E, but not F. Triangle inequality. So for the triangle inequality, 2 sides of a triangle, if you have 2 sides, there's only so long that that 3rd side is able to be. So I'm going to demonstrate this for you, and I was looking around my room for how I can demonstrate this triangle inequality, and you guys are going to laugh at me, but I can use a piece of my celery. So this is going to be the legend of the triangle inequality. And what's something else that I could use? I have a pen. Okay, I'll just use my pen as the other side of the triangle. So, given that these two things are fixed lengths, ooh, my nail polish is all chipping off. Wow, this is embarrassing. Okay, anyways, so I'm using celery and chipped off nail polish. Whatever. So if you have, so for the triangle inequality, you've got two given sides that are fixed, right? I can't make the celery any longer. I could make it shorter by eating it, but and then this other one is also fixed. To make different kinds of triangles, like that would be one kind of triangle, and then I would connect this other side, like that would. I could have another triangle, and then this other side would be that big, or I could make this angle in here a little bit smaller and make another different triangles that I can make with these two sides. But my question is well, how possibly be? There's like a smallest that it could possibly be here. That'd be like if I made this even a little bit smaller in here, tiny triangle going on, and then if I connected those two, like I think that's as small as this third side could possibly be. Because as soon as I start increasing this, this angle up here, then notice that this third side here is going to get longer and longer and longer and longer and longer, right? To be able to make the third side of my triangle. So what's the shortest that this third side could possibly be? Well, here, okay, it's pretty long, so I can make it get shorter and shorter and shorter and shorter. Well, what's the shortest that it could possibly be? The shortest that this thing could possibly be is tiny up there, right? When I make it as small as I can possibly make it, like maybe something like that, okay? So that's about as small as I can possibly make it. Well, how short is that? Well, if you kind of are looking here, it's kind of like the distance from here to here, right? It's like the difference between this length and this length, only it needs to be just a hair longer, because technically if it was the exact difference between these two pieces, then like that would be my triangle like that. Well, you can't really have a triangle that looks like that, because there's no side to connect. They're just, so it doesn't quite make any sense. But if I go just open up just, yes, now I have a triangle, and that side, now it's the shortest that third side could possibly be. So it's really the difference of these other two sides is the shortest that this third side could be. Well, what's the longest that this third side could possibly be? Well, if I take this and I make it bigger and bigger and bigger, right? It's increasing in size for this third side, and I make it larger and larger and larger. Okay, well, at what point does it get so large? Like that's pretty large, and I got a big triangle going on right there. I can make it even larger. Check it out. It's getting bigger. It's still getting bigger. At what point does it get so big that I can't do anything anymore? Well, now it's really big. Keep going. Okay, it's kind of a weird little triangle, but it is in fact a triangle. I'm getting bigger and I'm getting bigger. At what point does it get to the point where I can't make a triangle anymore? Right here, I mean that side's pretty big, but I can still make a triangle with a third side here. At what point am I the biggest I can possibly be and still make a triangle? Would be like, right? Okay, I just made this angle right here like as big as I can possibly make it, and I can still make a triangle in there. It's kind of a weird triangle, but I could still make a triangle, and that third side would be really, really large. At what point do I not make a triangle anymore? As soon as this gets to be perfectly in line with my other side, with my piece of celery here, then this third side, like I can't make a triangle anymore. So really, how long is this third side going to be? Well, at the longest, it can't be the distance from here, the end here, all the way to this end over here. It's got to be something just a teensy tiny bit shorter than that, and I can make that third side. So what's the longest that this third side could be? It's got to be something shorter than the sum of these two. And it's got to be, and then what's the shortest it can possibly be? The shortest it can possibly be is it's got to be the difference between these two sides. For helping me demonstrate this triangle inequality, I think I will eat you. Man, I bet you wish right now you had celery. I don't even care if you don't like celery. Right now you wish you had some. Alright, so the triangle inequality. The sum of the lengths of any two sides of a triangle is always greater than the length of the third side. And if this is not so, then the triangle cannot be made. So this is exactly what we were getting at just a second ago. What's the longest that this third side could be? What's the shortest that that third side could be? If I know that this length and this length have to be 9 and 15. There's all kinds of different triangles I can make by moving like this piece down or moving it maybe upward or something like that. And that's going to change the length of this third side right here, but what's the longest and what's the shortest that that third side could possibly be? As we mentioned with the celery and my pen, if you add these two sides up together, this third side's got to be something smaller than that. Or if you subtract those two sides together, again, this third side has to be something larger than that, which is what this is getting at. So what values can x take on? Well, how big is too big, at which point I can't make a triangle anymore? Well, if I add the 15 side and the 9 side together, my third side's got to be something smaller than that value, or x would have to be less than a distance of 24. Well, that's the top end of it. What about the bottom end of it? Well, the difference between those two, my value has to be something larger than their difference. So 15 take away 9 would be a difference of 6. My third side has to be larger than 6, but at the same time less than 24. So can x possibly be 11? Yeah, 11's a number between 6 and 24. Yeah. Okay, can x be 25? No, x has got to be a number less than 24, so it cannot be equal to 25. Could x be the number 6? No, x could not be the number 6. It's got to be something larger than the number 6, but it can't be exactly equal to the number 6. If it was exactly equal to the number 6, then I'd have my triangle would look like there's my 9 piece, and then there's the 15 piece directly on top of it. They're literally on top of one another. How are you going to make a triangle with that? You can't. Okay, you've got to have some kind of space between them. Cool. Assumptions. There's a lot of things in geometry you cannot assume. There's a couple of things that you are allowed to assume, but for the most part, there's a whole lot of things that you are not allowed to assume. Excuse me. Some things that you can assume. You can assume straight lines and angles. You can assume that if I draw a picture like this, I'm not trying to fool you and say, oh, that was actually 179 degrees. No, really, that is 180 degrees. That's really one single straight line. Okay, I'm not trying to fool you. You can assume that. A collinearity of points. You can assume that if I have a picture that looks like that I'm not the best drawer, but you can assume that, yeah, those are collinear with each other. I'm trying to draw them collinear. That celery is stuck in my throat. Betweenness of points. You can assume that this point is between these other two here. You can assume that. So what are some things we can assume? Basically anything else. You cannot assume an angle is a right angle. Just because something looks like it's 90 degrees, it looks like it's a right angle, unless they have the box there or they tell you, you cannot assume it's a right angle. You cannot assume that two segments, they look the same size, or two angles, they look the same size. Just because two segments and two angles, or I guess this would be segments, two segments look the same size, or two angles look like the same size, you cannot assume that they are the same size unless they tell you. You can't assume how big those sizes, the angles or those segments are. Just because that angle looks like it's 45 degrees, you cannot assume that it's 45 degrees unless you can prove it or they tell you. So when can you assume a right angle? Pfft, practically never. Well, you can assume it when there's a box. When they've drawn in the box for you, you can assume that's a right angle. Or if they tell you it's 90 degrees. Then you know it has to be a right angle, obviously. That's the definition of a right angle. When can you assume segments and angles are congruent? Very rarely. Unless they tell you that their measures are congruent. So they say this one's 30 degrees and this one over here is 30 degrees. Then you can assume that, yeah, those angles are congruent. Or the other way you can tell that they're congruent is when they have the tick marks. They have the tick marks and they are congruent to each other. So given, this is a ratio problem. Given these two angles are in the ratio of 7 to 2, find the measure of angle XYZ. So ratio means how many parts that they have. So this first angle up here apparently has got 7 parts to it, and the second angle down here has got 2 parts to it.